Okay, everybody, let's get going on lecture 7. We are racing through the quarter. And really for the rest of the 3 lectures before the midterm, we're really going to focus on atmospheric moisture, water vapor, clouds, the processes that result in precipitation, either rainfall, snowfall, some of those other forms. So, let's talk about the midterm. So I'm afraid the midterm is coming up next week. It's not this Thursday, so don't panic. It's next week. But I wanted to give you some warning about it. So it'll be on Thursday of next week in this room, as normal, from 2 to 3:20. I like long exams. Those of you who've had me before will know that. And so please do make sure that you come in on time and make the most of that. It'll be about half multiple choice, but half of it will be short answer in the form of making a small calculation, writing me a couple of sentences of explanation of something, or writing something on a map, drawing something on a graph. Those sorts of things that prove to me that you're a scientist after all. It'll cover everything, including the Tuesday's lecture of next week, which is relatively straightforward. So I like to include that one. It is assigned seating, so please do email me by Monday if you would like a left-handed seat. And in general, this is a full classroom, so I'm going to have to put right-handed people in left-handed seats, unfortunately. So if you are left-handed, please do let me know, and that way we won't have to put too many right-handed people in uncomfortable seats. Things that you will need. You will need a pen and pencil. Please don't bring calculators. There are no calculators allowed. You won't need to do complicated maths. A Scantron Form 288, it's the red one, you can get it from the bookstore. Student photo ID, which is standard for a big class like this. And, optionally, you can bring a little 3x5 note card, 2-sided, of notes to the exam, because I know that there are a lot of new words for a lot of people, and what I want you to focus on is the concepts. I don't care if you can repeat my slides back to me word for word. If you don't understand it, you're not going to do well. So please do focus on understanding. A study guide will be available on the website later today, so take a look out for that. You can always access your quiz answers. I hope you've been doing that as we go along. And for quizzes 1 to 3, I'll reopen those again later this afternoon, and you can go back and practice those as many times as you like. So if you didn't complete them before, you'll have a chance to see the questions. In addition, next Thursday, before the midterm, I'll be in my office from 10 till 12. So if you have any last-minute panicked questions, then I'd be happy to go through things with you. Okay? So are there any questions about the midterm? Not yet? No one's thought about it yet? Okay. As another reminder, because it's not on the schedule, there will be a midterm review session. It'll be next Wednesday from 5 to 5:50. In PCB 1100. So bring your questions for the TA, and they'll help answer those and go through things that you don't understand. Okay? Great. So let's review from Thursday, because Thursday started getting a little bit more complicated, right? We were talking about winds and pressure. And there are some very basic rules that govern the movement of winds. And by the end, you guys were getting the hang of trying to predict where those sort of pressures were and how wind would move. So first of all, wind goes from high to low. If you can remember that air rushes out of a balloon rather than into a balloon, then that's pretty simple to remember, okay? It's not something you need to occupy space on in your card. Horizontal winds are influenced by 3 things. First of all, we need a pressure gradient. If we don't have a pressure gradient, then we're not going to get movement of air. So first of all, we need that pressure gradient in order for air to start moving. The second thing that we need to take into account is the Coriolis force. Ideally, we would be on a completely stationary Earth, and then that would make our life a lot easier. But we're not. So we have to deal with the Coriolis force. And this changes the direction only. Doesn't change the speed of that wind, but it does change the direction. And so to us in the northern hemisphere, that wind will veer, it will be deflected towards the right, at 90 degrees to the right of the direction of travel. So remember, you always have to look along the arrow, along the motion, and then it's traveling at 90 degrees to the right of that. And in the southern hemisphere, it goes to the left. And so my stupid way of remembering it is that I'm from the northern hemisphere and I'm always right. And so if you can remember that, you can remember the Coriolis force. And then the third thing is friction. So friction affects the speed of the wind. The more friction there is, the slower those winds will be. So then let's think about what's happening. So vertical winds, we do see this vertical pressure gradient, but the force of gravity acting in the other direction means that we reach this balance, this hydrostatic balance. So we don't see very vigorous vertical winds. We see small vertical motions every now and again, but we don't have sort of gale force winds rushing upwards the whole time. And then we have our three layers of the atmosphere. We have the laminar boundary layer, which is the 1 or 2 millimeters, the tiny, tiny layer closest to the Earth's surface. And we're not going to talk about winds in that layer because it's only a couple of millimeters, okay? But we do care about the planetary boundary layer, which is the lower sort of 1.5 kilometers, and that's where friction is important. That's where there's things to bump into. So there's trees, there's buildings, there's mountains, there's other stuff that wind collides with, and it causes friction and it slows it down. And so that also reduces the amount of Coriolis force it feels. And then in the free atmosphere above that, then that wind, those moving air molecules really aren't moving or bumping into anything, and so there's sort of negligible friction. We can basically ignore friction up there. And what that means is that we end up with winds that are in balance between the Coriolis force and the pressure gradient, and so they tend to go parallel to those isobars. Okay? So that was one of the questions in the quiz this week. So that's our little summary. So in the free atmosphere, our winds move parallel to those isobars, but down at the surface, we see something a little bit different. When we have a high pressure at the surface, wind is going to go from high to low, and so it's going to move outwards and it's going to spiral out across those isobars. And so where we have wind spiraling outwards, we're not going to create a vacuum at the surface. We're going to have to bring air from somewhere to replace it. Now we're at the ground, so we can't bring air up from underneath. Wind is moving outwards in all directions. The only place we can get more air is from above. So as those winds move out at the surface, air is brought down from above, okay? And you can see that this is called an anticyclone, and we tend to associate this with nice clear skies. We live under a nearly permanent high pressure area here in Southern California, especially in the summer. And so this is why our skies are beautiful and clear. We live in a very dry area. In contrast, if we look at low pressures, low pressure, we have air moving from high to low. It's moving inwards at the surface from all directions. And we're not just going to keep piling air up in the middle forever. It's going to have to go somewhere. It can't go down because we're at the ground surface, and so it's going to go up in the atmosphere. Okay? So as it goes up, then it's cooling down, and we actually produce clouds and rainfall at these low pressure areas. Okay? So that's when you hear of a low coming in, we know that it's going to be pretty miserable weather. So we got to this point last week, but we didn't have much time to talk it through, and I wanted people, having had a chance to review their notes, to actually have another think about this, and we're going to do it in reverse. So, do you remember my beautiful, not that one, this one, my beautiful wind maps from this lovely website? Okay, so my challenge for you, I want you to find me at least one low pressure area. I want you to find me at least one high pressure area. Okay, so look at how the winds are moving around there. I want you to find me an area where the isobars will be far apart, and I want you to find me an area where the isobars will be close together. And think about where it's likely going to be raining as well. Okay? So I'll give you a couple of minutes to do that. The TAs, wave at me, TAs. 1, 2, 3. So they'll wander around as well. So find me a high pressure, a low pressure, where the isobars are far apart, where the isobars are close together, and where will it be raining? 5 things. Okay, so I had some really good answers over here. I think people are getting this. So, does someone want to point out to me the rather obvious area of low pressure? It's difficult to point, right? But hopefully, most of you would agree with me that this is a lovely, beautiful area of low pressure. Okay? And what about that told you that it was a low pressure? So it's spiraling counterclockwise, absolutely. So it's going in and to the right. So it's spiraling counterclockwise. And what else? The more obvious one. Spiraling inwards, yeah? So it's moving from high to low, it's moving inwards. Does anyone know what that actually might be? It's not Hurricane Katrina, it is actually Hurricane Isaac from 2012. But it's a hurricane, and you can see even that nice eye in the middle, right? Which is really cool. Can anyone point out to me an area of high pressure? Where do you think high pressure might be? Yeah, I think so. So one enthusiastic person at the front. Yeah, absolutely. Maybe over the Great Lakes. Can you see over the Great Lakes and around that, we have air moving outwards from there? And so that's more likely to be a high pressure area. Also near Phoenix, someone pointed that one out to me. You can see air moving outwards in all directions, okay? Where would we see the closest isobars? Gosh, you're all so quiet. Where would we see the closest isobars this side of the room? Yeah, near that area of low pressure, near the hurricane. Got fastest winds. This side of the room, point out to me another area where we'd see isobars really close together. In the middle, yeah, at the top in the middle, okay? So where do you think would be a safe bet that it's probably raining? Where the hurricane is, okay, absolutely, so it's not a shock. Okay, so let's have a quick look and see if we're right. So this is a complicated looking map. So I want you to ignore, first of all the crazy colored lines and shapes. But you can see that we do indeed have this high pressure over the Great Lakes. We have this high pressure north of Phoenix. We have this amazing low pressure system down here where the hurricane is, these lovely rings. We have a low pressure up here. We have isobars in the middle near the top, which are really close together, as do we down here. Okay? And you can see that these other areas where we didn't have strong winds, those isobars are nice and spread apart. Okay? So it's starting to make sense, hopefully. You're starting to see how these things connect. I think it's nice to be able to visualize that. And that green area does indeed show rain in substantial amounts of it. Okay. So hopefully everyone's getting to grasp this. And we'll come back to these again after the midterm when we talk about these other crazy sort of colors and symbols on there, and we talk more about sort of what our weather is like. But today we are going to move on to talking about moisture, and it's really very much connected with those ideas of highs and lows. We're going to explain a little bit about why the air warms up and cools down. So things that I'd like you to be able to do by the end of today are be aware of the steps of the hydrologic cycle, which a lot of you will have seen in elementary school onwards, and that they're really important in driving weather and climate at all scales, both global and regionally. Understand and be able to describe evaporation, condensation, saturation. We're going to know the main ways of quantifying atmospheric moisture content, because actually we use a whole bunch of different ones for different reasons, and we'll go through some of those. Describe 3 ways of saturating air. How do we get air so sort of saturated with water vapor that we start getting condensation in clouds and rainfall? And then we're going to talk about diabatic versus adiabatic processes. And I'm going to do my magic trick, which a lot of you have seen before. Okay, so first of all, why do we care so much? Why am I going to speak for 3 whole lectures about atmospheric moisture? Because we need it. All life needs water. And our lifestyle especially depends a huge amount on the amount of water. So does anyone want to, someone not from my ESS 21 class that just heard this, so does someone want to give me an estimate of how much water they use in gallons per day? So turn to your neighbor and tell them how many gallons of water per day you think you use here in Orange County. Okay, so does someone want to give me an estimate? How much water do you think you use a day? So middle section, I haven't picked on you yet today. How much water do you think you use? Someone give me a number. At the back, yes. 150 gallons. Pretty close, but up a bit. actually 176. I'm very impressed at how close that is. The average resident in 2005, and pretty similar to today probably, used 176 gallons. And it's not because they took 2-hour showers every day. It's because a lot of our water use isn't just what we drink, it's not what comes from the taps, it's hidden water. So my first question for you is, which of these things do you think takes the most amount of water? So running your dishwasher, if you're lucky enough to have one, for a month. Manufacturing a cotton shirt, an 8-ounce steak, or 1 cup of coffee. So what do you think takes the most amount of water? And for those of you who've had the class before with ESS 1, you should be able to remember this. Okay, let's take a look and see how much you know about hidden water use. So it's a 3-way split, and I will tell you that if you voted C, you were correct. That is how much water it takes to produce 1 8-ounce steak, 1,232 gallons. But B wasn't far behind. It takes 1,083 gallons to produce a cotton t-shirt. So a lot of that water that we use is hidden. It doesn't mean that we're not using it if we just sort of save water from the taps. That's also important. But also we need to think about the rest of the water that we use per person. So water is important for us. It is also very important for the Earth system. So 70% of our Earth's surface is covered by water. Our oceans are amazing resources for us. Do you remember we talked about the high specific heat, that it takes a lot of energy being added or lost to change the temperature of our water, and so the oceans help stabilize our climate system an awful lot, especially at the coasts. Water vapor is a really powerful greenhouse gas. It really is the most significant in terms of creating our greenhouse effect. And remember that that's a good thing. If we didn't have the greenhouse effect on Earth, then we would be sort of frozen solid. We wouldn't necessarily have life on Earth. And also, water is really unusual in that it's really one of the only substances, if not the only substance, that naturally occurs in all 3 phases, in solid, liquid, and gas, here at Earth's surface, which I think is really fun. And more important is that the absorption and release of that latent heat as we change those phases is incredibly important for our climate and for moving energy around the world. Okay? So this is our hydrologic cycle, and I think most people saw this from sort of elementary school onwards, but very sort of quickly, we have evaporation from our oceans, which is by far the most dominant way that we get water vapor going into our atmosphere. I mean, 70% of the Earth's surface is water. It's going to contribute a lot of that water vapor in the atmosphere. We also get some evapotranspiration, which is sort of through plant leaves and things like that from the land. And then once it's in the atmosphere, if it cools, we can get condensation forming clouds, and those clouds can move, that water vapor can move, and then we get precipitation over the ocean again, or over land. And over land, if it falls in the mountains as snow, it can stay there a very long time. If it doesn't, if it falls as liquid water, then it either forms lakes and streams, or it goes into vegetation, or a lot of it actually goes into groundwater, into the spaces in between the rock and soil that make up our sort of solid Earth. And then it sort of gradually flows back to the sea. So it's basically a closed system. We're not losing water anywhere along the way. We're not gaining water. If we change the amount in one place, we change the amount in another place. Okay? And so this is one of the problems when we have ice sheets melting. That water just doesn't magically disappear. It raises our sea level. It's being returned to the ocean. Okay? So this is our hydrologic cycle. And really, we're going to talk about the evaporation and condensation process today. And then we'll talk even more on Thursday and next Tuesday about condensation and precipitation especially. So, review for anyone that has been sleeping for the last 2 weeks. We have solid, liquid, gas. And you may be quite familiar with the processes of freezing and melting, and evaporation and condensation. But there are two that you might not have heard of, and that is we can go straight from solid to a vapor or a gas, and that process is called sublimation. Sublimation. And we can also go straight from gas to a solid, and that process is called deposition. So, has anyone been up in the mountains overnight and it's got very cold, and you've walked outside and seen frost? A few people. Everyone's from Southern California. Okay, well, it gets frosty in cold places and elsewhere, and that's a good example of deposition. We're going straight from atmospheric water vapor into ice. How about, has anyone ever played around with dry ice? Yes, everyone's played around with dry ice. Okay. Does it form a liquid, or does it go straight from solid to gas? It just goes straight from solid to gas, right? It's sublimation. Okay, that's the name for that process. Okay? And so remember, we're going to talk about sensible heat and latent heat a little bit today. So sensible heat is that transfer of energy which causes a change in temperature. It's what you experience if you go and put your hand on the concrete outside. It's got warmer throughout the day because it's receiving energy from the sun. Latent heat is that stored energy, okay? And so energy is sort of required to change the phase of the substance. Doesn't change its temperature, it just goes from liquid to solid or from solid to gas, those sorts of things. Okay, so let's talk about evaporation and condensation. It's something we're very familiar with, but let's think at a more molecular level about what is actually happening. So I have three little diagrams at the top of my slide there. So let's start on the left, first of all. So on the left, I have a sealed can, and I have liquid in the bottom, I have water in the bottom, and just sort of airspace in the top. And we've created a covering over the surface. So right now, all of my water is in the liquid form. There's nothing in that airspace at all. So what happens if I remove that covering? Well, the process of evaporation is actually just those little water molecules escaping from the surface of the liquid. They gain enough energy to escape from the surface of the liquid, and they start moving around freely in the airspace. That's our process of evaporation. When we talk about condensation, all that's happening is that the random motion of those molecules in the atmosphere means that sometimes they recollide with the water, and that's condensation. It's rejoining the water. So as we take our covering off, there are no water molecules in the airspace, so how much condensation is happening? Come on, guys, you can do this. So how many molecules are in the airspace to begin with? None. So how many are going to be able to recollide with the water surface? None. Okay, so we're not going to have any condensation to begin with, but what we are going to have lots of is evaporation. As soon as that cover is removed, we're going to have water molecules escaping and moving into that airspace. Okay? So what happens at first is that our evaporation rate is much larger than our condensation rate. And so water molecules start to build up in that airspace. Does that make sense? Yeah? So that continues until we reach a certain point. That will continue until we have so many water molecules in the air that now more and more and more of them are colliding with the water surface. And at a certain point, we hit saturation. And at that point, we have equal amounts of water molecules escaping the surface. And because there are so many air molecules already in the atmosphere or in the air, we have equal numbers colliding with the surface. So our evaporation rate is going to equal our condensation rate. Is the absolute number of molecules in the air at that point ever going to change? No, because we're putting equal in to equal out. Okay? So it's at equilibrium, and that's what we call saturation. And that saturation, basically the amount of water molecules we can get into that space, changes depending on the temperature. So what do you think will happen? As we increase temperature, do you think we can get more water vapor molecules in there or less? More. We've got those molecules, they have more energy, they're escaping more rapidly from the surface. Okay, so we get higher evaporation rates, we can get more water vapor molecules in that airspace. Okay, so let's have a look at some of my definitions here. I've already touched on a couple of them. So when I talk about vapor pressure, what I'm talking about is the pressure of a gas above a liquid. So for example, in my first diagram on the left, there would be no vapor pressure because there are no molecules to collide with the walls and create a force. Okay? In my middle diagram, I have a few water vapor molecules, and so as they move around, they're colliding with the sides, and so they'll create a little bit of pressure. So we'll have a little bit of vapor pressure. In my third diagram, I have a lot of water molecules. Okay? So they're all going to be moving around and colliding with the sides. They're going to create a higher vapor pressure. Does that make sense? Yeah, hopefully. And when we're at saturation, the vapor pressure at that point is called the saturation vapor pressure. And we're going to talk about that later today. So that's the vapor pressure exerted by the molecules when we're saturated, when there's the maximum number of molecules in that airspace. Okay? So is that okay with everyone? I don't want to move on until that makes sense. Yeah? Everyone's completely still. Okay. So let's talk about vapor pressure. This is our first way of quantifying atmospheric moisture. Okay? So really we talked about this. The fewer molecules are, the lower the pressure. The more molecules there are, the higher the pressure. Okay? And so here is a little graph showing that. Okay? So on the y-axis we have vapor pressure in millibars, which is, remember, just a way of measuring pressure. And we have temperature in degrees Celsius along the bottom, going from very, very cold on the left to pretty warm on the right. And you can see that I've drawn a red line on there. Okay? That red line marks the pressure, the vapor pressure at which that air would be saturated at those different temperatures. So if I went to maybe 0 degrees Celsius, if I wanted to know how much vapor I could possibly have in that air above something at 0 degrees Celsius, it would be maybe 5 millibars. Okay? So at 5 millibars, I would be saturated at 0 degrees Celsius. At 0 degrees Celsius, I would need 5 millibars of water vapor to be saturated. Does that make sense? So what happens if temperature increases? What happens then if I change the temperature of my little sealed container and I make it, I don't know, 30 degrees Celsius? What's going to happen? The pressure will increase. And why is that pressure increasing? Because there's more evaporation going on. Okay, so there's more evaporation, there's more water vapor molecules in that space, and so we can sort of have more evaporation happening. So what happens if I decrease that temperature, if I go from maybe 0 degrees Celsius to, I don't know, minus 10 degrees Celsius, and let's ignore the fact that it would be frozen at that point? What would happen to some of those water vapor molecules? We'd get condensation, right? So we'd condense. So what happens now if I added more water vapor? If I just injected some extra water vapor into the side, what would happen? You have only two options. Are we going to get more evaporation or more condensation? Condensation, because again, there's going to be more collisions with the water than there are molecules evaporating. So if you've heard of supersaturation or unsaturated, this is sort of this idea. So what we can look and say, if temperature increases, okay, so here's my little parcel of air. It happens to be at 20 degrees Celsius. It has 20 millibars of vapor pressure. If I increase that temperature, then more evaporation can take place. And so it's called undersaturated or unsaturated. So anywhere under that line is unsaturated. We can have more evaporation. But if I do either of these other two, if I decrease the temperature, so if I move that sort of circle to the left, or if I add more water vapor, if I move that circle up, then we're going to be supersaturated. We're going to have more water vapor molecules colliding back with the surface, and we'll have more condensation going on. So, at what temperature would the parcel of air on there, so it's sort of at 30 degrees Celsius, about 10 millibars of vapor pressure, At what temperature would that parcel of air become saturated? Well, half of us agree. I think so. So what am I going to do? I'm going to look at what temperature. We're not changing the amount of water vapor, so we're not moving up and down on my graph. All we want to look at is left and right. And I want to see at what temperature it becomes saturated, so at what temperature it would hit that red line. And so if I draw a line across, I see where it would cross that red line, and then I read down, and so you can see that that would be 10 degrees Celsius. Does that make sense now for those that didn't get it? Yes? No? Okay. So that 10 degrees Celsius there, that sort of temperature at which that air is saturated is something we call the dew point temperature. That's the temperature that air would have to drop to create dew, that's sort of the water that you find outside on surfaces in the morning after you've been outside. Okay? So that temperature, that dew point temperature, is that air temperature at which a parcel of air will be saturated. Okay? And it's always less than or equal to the actual temperature. So that's a good independent check if I ever ask you that question. And the higher the dew point temperature, the more moisture. So let's go back. So if I change my mind about how much water vapor was in my air, so my little air parcel had a water vapor pressure of maybe 10 millibars. So what would the dew temperature be if it was 20 millibars? At what temperature would that air be saturated? 20, yeah. So again, you follow it along. So if my air parcel instead started at, say, 20 millibars, I'd again just follow along until I hit that red line, and then I read down, and it's about 20 degrees, okay? So the more moisture there is, the higher the vapor pressure, the higher that dew temperature will be. And it's a nice measure because we can plot maps of it really quite nicely, okay? So it's a very useful measure of water vapor abundance. So here shows a little map showing you the dew point temperature over the US in the winter, okay? So those darker purple colors are the colder temperatures. So is that less or more moisture? So the colder temperatures are less, okay? Yeah. Now let's look at the summer, and you can see that there's a really different pattern, okay? So where is there a higher amount of moisture at this time of year? Florida, the East Coast, okay? Feels humid, right? So my second question of the day, does California have higher amounts of water vapor in the air in the winter or in the summer? So there's a 50-50 chance. So see if you can use those maps and work it out. Okay. 6337. So summer is right, okay? So don't go with what you think you know, go with what the maps tell you, okay? And you can see that we have paler colors, so paler greens, yellow sort of colors. We have higher dew point temperatures in the summer compared to the winter where we have those darker greens, those sort of blues, those colder dew point temperatures. So actually we have more water vapor in the air in the summer. Does it feel damper in the summer, or does it feel drier in the summer? It feels drier in the summer. So there's something that this sort of measure of atmospheric moisture isn't taking into account. Because actually what we feel in terms of is it muggy, is it humid and everything else, is a relative humidity. How much moisture is there compared to what there could be? And this is something when the Santa Ana winds blow, right, it feels really dry and your lips crack and your skin feels really dry. And that's because there's a very low relative humidity. There's very little water vapor compared to what there could be in that very warm air. Whereas in the June gloom, that sort of time, it's sort of very sort of muggy, it's sort of more humid, and that's because there's a lot of water vapor compared to what there could be. So the way we use to describe this is relative humidity. We have a little formula, okay? So the amount of water in the air is expressed as a percentage of what it could be. So if you've heard of, say, the relative humidity is going to drop to 10% today or something like that, that's sort of what we're going to calculate now. So my relative humidity is equal to the actual vapor pressure, so what is really in the air compared to this, or over the saturation vapor pressure. So what could there be in the air? Okay, and that times 100 to get it into a percent. So I have a little example to begin with, and then you guys are going to have a go. So first of all, my actual vapor pressure. So you can see that my little blue dot marks my parcel of air again. And so you can see that it's at 20 degrees, and it has a vapor pressure of 10 millibars. So the actual vapor pressure here is going to be 10 millibars. That's what's really in the air. Okay? But what could be in the air? So at what point do we become saturated at 20 degrees Celsius? Well, you can see if we draw a line up from 20 degrees Celsius, we hit that red line at about 20 millibars. So we could potentially have 20 millibars of vapor pressure before we hit saturation. Okay? So 10 divided by 20 times 100% is 50%. So not too tricky, right? So let me know what you think. So my parcel of air is at 30 degrees Celsius, and it moves over the sea, so my water vapor pressure now increases to 20 millibars from what it was before. What is the relative temperature or relative humidity in the dew point temperature now? So I'll give you a couple of minutes to think about this. So remember that my formula is relative humidity equals the actual divided by the saturated times 100%. Right? Let's see how we're doing with this. Oh, we're doing pretty well. 70% of us have the right answer. So let's have a quick think through this example for those that might still be a bit lost. So the temperature of my air is 30 degrees Celsius. So here's 30 degrees Celsius, and I have 20 millibars of vapor pressure. So my little parcel of air is going to plot about here. So first of all, let's do dew point temperature. If I, again, just follow along, okay, we can see that my dew point temperature is about 20 degrees. We looked at that example before, okay? So first of all, that's already narrowed it down to B. But anyway, let's continue and do the full thing. So here's my vapor pressure, and that's my actual vapor pressure. That's what's actually in the air, that 20 millibars. But at 30 degrees Celsius, what could we potentially have? So if we follow a line up from 30 millibars, then we can see that we could potentially have 40 millibars if we want to hit saturation vapor pressure. So 20 divided by 40 times 100% is 50%. Okay? So does that make more sense now? So sometimes it takes a little bit of practice. So go and have another look if you didn't quite grasp that. It should make sense. So relative humidity, it's helpful because it's what we feel. And why do we feel that? Because if we get up to sort of very, very high humidity, very, very high relative humidity, at that point, it's very difficult for our sweat to evaporate. Okay? And remember, it's the evaporation of that sweat that carries energy away from it. We need to, that energy is required to go from being a liquid to a gas, and that energy comes from our skin, and that's why the evaporation of sweat is so good at cooling us down. But if we get to the point where what's in our air is very close to being saturated, then it's difficult for that process to happen, and so we're not going to lose energy from our skin, we're not going to cool down. Okay? So that's why relative humidity is so helpful. It's actually what we feel as a result, okay? But if you plot it over a day, then that's what happens, because our temperature changes. And here in California, it changes a lot between the middle of the day and, say, the evening and the middle of the night. And so what happens is that our relative humidity, even if the amount of moisture in our air isn't changing very much, because the temperature changes, the saturation vapor pressure changes, and so we get really big changes over the day in our relative humidity, okay? But it does help us realize what it's going to be like. So others that we're not going to get into, but there are a whole bunch of others that meteorologists find helpful. They include things like mixing ratios, specific humidity, absolute humidity. we're not going to touch on those. We're really going to focus on these three first ones, okay? So let's have a look at how these things are measured. So we're going to look at how relative humidity is measured.
Trainers are responsible for the player's health, from injuries to hydration and so much more. But the weather in Mississippi makes things different.
The humidity is a big factor with us because when you have the humidity, it doesn't allow your sweat to evaporate. So you're holding that heat in your body, whereas in a cooler environment or an environment with less humidity, that sweat's able to evaporate off of them and cool them off.
Since humidity can impact a player's health, the trainers are routinely checking the exact humidity in the air. They gather this data by using a sling cyclometer. This little gadget measures the dry air temperature and wet bulb temperature to formulate the humidity.
Now we sling it for about 5 minutes. And after that time's up, we'll take it and get our readings off of here. We get a dry reading, which is the dry air temperature, and also a wet reading. And we take those two readings, slide it into this neat little slide rule here. We take our wet reading and our dry reading and line it up, and the arrow points to the relative humidity.
Depending upon the humidity, the trainers can then determine how to treat the players to avoid dehydration and heat illnesses.
It sounds simple, but we encourage them to take their helmets off when they're not on the field.
So anyway, if you're an American football player, you can continue watching that. But for us, so that's how you measure it, and it looks ridiculous, right? So my question for you is, so we just had 2 thermometers. One of them was just a normal thermometer and he was swinging it around in the air. But the other one had like a little piece of cotton cloth soaked in water at the end. So what would happen to the temperature of the one that had sort of the water at the end? Why would they be different? Sorry? Is it specific heat or the other type? Latent heat. So you got to start it definitely. So what's happening as he swings this thing around, if there's sort of water on the end of one of those thermometers, what is happening? So we're getting evaporation, right? So, and what's evaporation doing to the temperature of the thermometer? What does it do to your skin? It cools it down. And so the amount of evaporation that's happening at the end of that thermometer as he swings it around is a measure of how much evaporation is going into the air. And the amount of temperature change that you see will tell you what the humidity is. Because if we're at 100% humidity, is there going to be any difference between the thermometers? No, because there's going to be no evaporation. Okay? If we're down at like 10% humidity, like during the Santa Anas, do you think there's going to be a small difference or a huge difference in the temperatures? A huge difference, because there's going to be a lot of evaporation, and that is going to remove energy as that water goes from a liquid to a gas. We need to put energy in. Okay, does that make sense? Okay, you guys are really hard work today. Come on, it's exciting. So, thank you. Let's think about how we can saturate air, because really if we want to go to the next step, we've had evaporation, if we want to go to the next step where we get clouds and we get rainfall, we need to saturate air. We need to find ways of getting that air to saturation. So there are 3 ways. First of all, we can just add more water vapor, okay? And that can be difficult to do over land. It's somewhat easier to do over the ocean. We can decrease the temperature of the air. And you can see that I've put this one in bold because this is the main one, and this is what we're going to talk about for the rest of today. And then we can just cheat and mix warm, moist air with cold, dry air. And you can see that if they meet and they cross that saturation line, we can call it saturated. So let's just talk about decreasing the temperature of the air, because that's really the easiest thing to do. That's the reason that most of our condensation happens in the atmosphere. So let's think about how to change our air temperature. There's lots of different ways. So first of all, we can absorb or release heat okay? And that can be by radiation. If we radiate energy away, then the temperature of that body is going to drop. By conduction, if that energy is transferred from a sort of hotter area to a cooler area. And sensible heat transfer, okay? Those are both examples of that. Secondly, we can just mix the air, which we've already just mentioned. But if we mix warm and cold air, we can change the temperature. So that's by convection, that's movement of the material itself. And then the third one is that latent heat exchange again. So we can change the phase of water. So if we condense water vapor, do we absorb heat or do we release heat? I even have it on there, releases heat, okay. And what about ice cubes? As ice cubes go from solid to liquid, do they absorb heat or do they release heat? Absorb heat, yeah, okay. So that's one way of doing it as well. So these three processes here are called diabatic processes. So we're adding energy to the system or we're removing energy from the system, okay? So the amount of energy in the system is changing and that changes the temperature, okay? So we have a different category of temperature changes though. This one is called adiabatic, and this one doesn't involve changing the amount of energy in the system. All that it involves doing is changing the pressure. So now we can start to see why this one might be really important for the atmosphere, okay? So the idea is that when we compress air, work is being done on the molecules, they warm up. As that air expands, work is being done by the molecules, they lose a little bit of that sort of energy and speed, okay? So compressing air heats up, expanding air cools down. And most of you have probably seen an example of this, because have you ever seen an air duster? Has anyone had an air duster to clean out their laptop and stuff? So what happens is you spray this. What happens to the can? It gets cold, yeah. So anyone that doesn't believe me can come down and try it at the end. But as you do this, through time, it gets really cold. So you can prove me right. Yep? Yeah. Independent check from the front there, I'm not lying to you. Okay? So that's an adiabatic process. We're not changing the amount of energy, but what are we doing? We're releasing material from in here, which is pressurized. So we're lowering the pressure in here, and that cools down. Okay? We're changing the pressure. So now, let's think about another example, okay? So for those of you from ESS 1, you've seen this before, but I have a plastic bottle, plastic soda bottle, and a bicycle pump with a stopper on the end, okay? So we're going to do a little thought experiment. I'm going to ask you two things. So if I put this stopper in here, and I start pumping air into this bottle, what am I going to do to the air temperature in the bottle as I increase that pressure? Increase it, yeah, it'll get warmer inside the bottle. What will I do? Sorry, make everyone jump. As I decrease the pressure, am I going to warm it up or cool it down? Cool it down, okay. So, now I have a question, which is, I'm going to add a little bit of liquid, okay? And I want you to think about what happens to the saturation vapor pressure as I warm up the air. What will happen to the saturation vapor pressure as I cool that down, as I release that pressure? And I want you and your neighbor to come up with a hypothesis of what might happen in the bottle, okay? So again, the TAs will wander around for a minute or so and see if you have any ideas. So I had some good answers from the back. So as I increase the pressure in my bottle, what is going to happen to the air temperature? It increases. What does that do to the saturation vapor pressure? Increases. So what might happen to some of the liquid in my bottle? What will happen as I decrease the pressure, as I release the pressure? It cools down. What happens to saturation vapor pressure? Decreases. So what might happen? condensation. So shall we see if you're right? Give me a second. Ugh. Okay, are you ready? Ooh, I made a cloud. Do you want to see something even more cool? What will happen as I do this? Okay, one more time. Everyone always says yes. Okay. Ready? Oh, it didn't work. Give me a sec. Okay. Okay, so we made a cloud. And why am I doing this, apart from just it's fun? Because this is one of the same processes that happens in the atmosphere. So what we're doing is down here at the surface, we have lots of water, we have compressed air, sort of down here we have higher pressure, which is warm, we have a high saturation vapor pressure, we have lots of evaporation going on. But if we can release that pressure, if we can lower that pressure, for example, how might we easily lower pressure? By making that air rise, by making it go up in the atmosphere. Remember, we have lower pressure as we go up. If we can force that air upwards, then we can release that pressure, we cool our air down, we decrease the saturation vapor pressure, we get a cloud, okay? So that's a lot of fun. And it's a demonstration that adiabatic processes are important in producing the condensation we see in our atmosphere. Okay. So, let's talk about the different forms of condensation. All of these are condensation in some way or deposition. So first of all, we have dew. And you can see that even here in Southern California, sometimes you go out after night and the air temperature has fallen low enough that we've hit saturation. We get water droplets forming on surfaces. If it's beneath 0 degrees Celsius, when that happens once we hit saturation, then instead of forming water droplets, we form ice crystals by depositing some of that water vapor in terms of ice. Okay, so if you live somewhere cold, you've experienced that. Here in California, you're more familiar with fog. It's really the only weather we get at certain points of the year. So we get things like the June gloom. If you've ever lived in San Francisco, you're very familiar with fog. I know that the Central Valley, you guys have fog days as well, right, rather than snow days. So fog is something we're familiar with, so let's look at some examples of that. And lastly, our most classic example is clouds. Clouds are an example of condensation. Okay. So let's think about types of fog. So we have lots of different types of fog. They form due to different processes over the US. And we have these three types. We have, first of all, radiation fog. And radiation fog is just forms because, say, overnight, for example, the Earth is giving out, it's emitting long-wave radiation. And it's not receiving any extra radiation from the sun. So as it gives out that radiation overnight, then the air cools down. The Earth cools down, the air above it cools down. And so eventually we hit saturation, and if that happens at ground level, we get condensation and fog. So that's radiation fog, and that's what happens in the Central Valley. Overnight, we lose that energy from the surface, and it's nice and still. And so we get that radiation fog. Advection fog is what we get here closer to the coast. It's what you get in San Francisco. And here, we're changing the temperature of the air. We're cooling that air down by moving it across a really cold surface. And where can you find a really cold surface in San Francisco? If you go out over the water. So if you have that air moving across the really cold ocean, it also cools down the air, and so we move closer to saturation. Once we hit saturation, if you're at ground level or whatever altitude you are, then you tend to get condensation and fog. And so that's important all along our coastline. And then lastly, we have upslope fog, which is something that's more important on the other side of the Rockies. And this is cooling of air as it flows upslope, okay? So as it moves up the hill. So hopefully, obvious question of the day. So thinking about those three mechanisms of producing fog, so which one of those fogs forms due to an adiabatic process rather than a diabatic process? So remember which ones those were. Look back in your notes for a second. Which one is which? Okay, let's see how we're doing. Close enough. So yes, it's C, okay? Because what is an adiabatic process? What is our definition of an adiabatic process? Yeah, a change in pressure, right? So if we think about A, the radiation fog, we're losing energy from the system, right? We're losing energy by radiation. That's why it's cooling down. So it's a diabatic process. If we look at advection fog, it's cooling down because it's passing along a cold surface. That's conduction or some sort of energy transfer. So again, that's a diabatic process, a diabatic process. So an adiabatic process, by process of elimination, is our upslope, because what happens as we move upslope is we get a change in pressure, okay? So as a quick reminder, this is what happens to pressure as we go up in our atmosphere. We start off nice high pressure down at our surface, but then we quickly lose that pressure as we move up. So anything where we're moving air up or down is going to be an adiabatic process, okay? So they're very important. This is one of the reasons that Santa Ana winds are so hot. We'll come back to this, but I think it's fun. Santa Ana winds are so hot, not because they come from the desert. They often come in from the desert in November when it's really cold out there. They're hot because they come from the high desert and then they flow down the slope into the LA basin. And as they flow down, they're compressing, so they really warm up a huge amount. So that's why they're hot, not because they come from the desert necessarily. So let's talk about how we form clouds. Because really this is what we need to do if we're going to make rainfall. So we'll talk much more about this on Thursday, but let's go through some of the steps for cloud formation. So first of all, let's start at the ground level, at the very bottom of my diagram here. You can see that my air at this point is 30 degrees Celsius, okay? It's down here close to the ground. There's probably a certain amount of sources of water around. So we're going to have a lot of evaporation. There's going to be a certain amount of atmospheric moisture in the atmosphere. And you can see that as we force that air to rise, so this isn't just measuring the temperature at different points in the atmosphere. We're taking that air, that little parcel of air at the surface, and we're forcing it to rise up in the atmosphere. And as it rises up in the atmosphere, it expands because there's less and less pressure, okay? And as it expands, it cools down. So you can see that for every 1 kilometer, so every 1,000 meters we go up in the atmosphere, it cools down by 10 degrees Celsius. It's a nice easy number to remember, a nice round number. So after 1 kilometer, my air that was originally 30 degrees is now 20 degrees. After another sort of kilometer up to 2 kilometers, then it's 10 degrees, okay? And so you can see how this is going to go. But at a certain point, at around 3,000 meters, 0 degrees Celsius, but it could be a different temperature depending on how much moisture there is in the atmosphere, it hits its dew point temperature, it hits a relative humidity of 100%, it's saturated. And at that point, you start seeing clouds. So if you go out today, if you look up in the atmosphere, that lower level of the cloud that's forming will be a saturated point, okay? And then we have something different going on, because we have water vapor turning into water droplets. So what happens as we go from gas to a liquid, is energy absorbed by the water or is energy released by that process? It's released. And so that energy is released by that process of condensation, and it goes into warming up the surrounding air. Okay? And so now we have two things going on. First of all, we have that air continuing to rise, and so it wants to continue cooling down at 10 degrees Celsius each kilometer. But we have this second process now, this release of energy by that condensation, and that's adding in energy back in. Okay? And so what we see is that the addition of energy back, it only adds in about 5 degrees Celsius. So we're losing 10 degrees per kilometer, and we're gaining 5 degrees. So now you can see that from when I start forming sort of clouds, from when I get condensation, my lapse rate, so how quickly I cool down in the atmosphere, is 5 degrees Celsius per kilometer instead. If that cloud wasn't there, it would still keep cooling down at 10 degrees. But because we're releasing latent heat, we start to see that change. Okay? So, I have a little challenge for you. Here is a little explanation of what I just said, but it's mixed up. Can you put the sentences in order to explain what I just talked about? Can you put them in order? Okay, so have a think through that. The TAs and I will wander around and give you a hand with it. So think about where it starts. So I'll give you the starting point. The starting point is number 2, okay? So my first one is number 2. What is my second sentence? Oh my goodness, I got one of everyone there. So I have a little group of consensus at the front that says 4. Would you agree with them? Yes? So that makes a certain amount of sense, right? As temperature drops, relative humidity goes up, because what's also dropping as temperature drops? Saturation vapor pressure. So saturation vapor pressure is also dropping, so our relative humidity rises as our temperature drops. And relative humidity rises until air becomes saturated. So it carries on to number 1. So our relative humidity will increase until air becomes saturated. What happens after air becomes saturated? I would agree. Condensation will start. Okay. What would be next? Number 6, that condensation process is releasing heat. And so therefore, 5, last one, we get this different lapse rate, this different rate of cooling as we go up. Great. So more on Thursday about clouds.